Hello, everybody. My name is Mironchenko. Welcome to my talk on Lyapunov criteria for stability of infinite-dimensional systems. This is an online version of the talk which was held at the Colloquium of the Department of Mathematics at the University of Bayreuth. I thank Lars Grune for his kind invitation to give this talk. Infinite-dimensional systems appear in many areas of natural sciences and engineering, such as aerospace engineering, climate modeling, population dynamics, biomedical applications, chemical engineering, etc. In many applications, we're interested in asymptotic properties of dynamical systems, such as forward completeness, which means global existence of solutions, local stability of equilibria or solutions, uniform boundedness of trajectories, that the trajectories starting in the bounded ball remain in this bounded ball, in some other bounded ball forever, or global asymptotic stability, which is most interesting for this talk. It turns out that it is hard to analyze these properties for nonlinear systems just by definition. However, the mechanics helps us. It turns out that for many mechanical systems, it is sufficient to know the dynamics of the energy of the system in order to know and to analyze the dynamics of its state. Lyapunov functions are a mathematical abstraction of the physical energy concept, and it helps to analyze all such properties. In particular, all these four concepts have the criteria in terms of Lyapunov functions. Today, we're going to revisit the very definition of a Lyapunov function. Namely, we would like to know which particular parts of the definitions are necessary and why. This talk will consist of two main parts. In the first part, we consider dynamical systems. These are systems without any external inputs, disturbances, controls, etc. And in the second part of the talk, we're going to study Lyapunov methods for so-called input-to-state stability of the systems with inputs. In order to formalize many of the notions that we need two classes of comparison functions, namely k-infinity functions, which are continuous functions, which are 0 at 0 and strictly increasing to infinity. And kl functions are functions of two arguments. In the first argument, they are 0 and 0 and increasing and continuous. And in the second argument, they are decreasing strictly to 0. Okay, so in this talk, we're going to analyze nonlinear systems. However, let us start from more simple case, from the ODE systems, to have some feelings on what we can expect. So we consider the classical ODE systems, x dot equals f of x, where f is a locally Lipschitz continuous function. This means in particular that the solutions exist and are unique for any initial conditions, well, at least locally. We will say that this system is globally asymptotically stable if it satisfies two properties. The first of them is local stability, and the second, global attractivity. So global attractivity means that all the solutions approach 0 when time goes to infinity. And local stability means basically that around the origin, the small deviations of the initial state induce only small deviations of the trajectory of the system at the whole real axis. It is well known that this system is globally asymptotically stable if and only if there is a KL function beta such that the norm of the trajectory is upper bounded by beta function depending on the norm of the initial state and time. So the larger the initial state, the larger will be the bound for the trajectory, this function, the value of beta. And the larger is t, the smaller will be the value of beta, and thus the smaller will be the bound for the trajectory. An important point here is that the dependence of beta solely on the norm of x means that the solutions starting in the bounded ball, or in any bounded ball, they have some minimal speed with which they converge to zero. And this follows from this, because, I mean, for any epsilon, we can find t such that this will be less than epsilon for all x from the ball of radius r, let's say. This is not so clear from the definition, because here global attractivity does not tell us that all the solutions approach zero with the same speed. It just tells that every of each converges to zero. But thanks to finite dimensionality of the state space, one can show that we get this uniformity of convergence on bounded balls for free. Okay, so now we have understood what is global asymptotic stability, and we need a tool how we can analyze this property for nonlinear systems. And this tool are Lyapunov functions. Namely, a continuance function is called a coercive Lyapunov function if there are two k-infinity functions, psi1 and psi2, such that v is sandwiched between psi1 and psi2 in this way, and also the derivative of v along the trajectory at any state x is negative, and there is with a decay rate alpha, which depends solely on the norm of the state. And now, so in particular, this means this second dissipation inequality, that if x is non-zero, if we are outside of the equilibrium, then the energy or the value of a Lyapunov function decays along that trajectory. And the importance of this concept is in this theorem that the ordinary differential equation is globally asymptotically stable if and only if there is a smooth Lyapunov function for this system. This means that if we have such a function, then we can show that the system is globally asymptotically stable. And conversely, if the system is globally asymptotically stable, then we always can find such a function, and so it makes sense to search for it. Okay, so this is what we have for finite dimensional systems, but we're interested in infinite dimensions. So let us generalize a bit what we have here. So we consider the systems in a Banach space X of the following form. X dot equals ax plus f of x, where f is still locally Lipschitz continuous function, and A is a generator of a strongly continuous semigroup on the Banach space X, which means that this linear system is well posed with a solution of this form. Okay, so if A is a bounded operator, then the solution for this equation is precisely the action of matrix exponential on initial condition, right? So where it is, or operator exponential, where it is defined in the usual way by Taylor series. If A is not a bounded operator, then this T of T has some more complex structure, but it is still satisfies semigroup property, and we still have such solution. Okay, so under these assumptions, we are going to study such systems. And first of all, we need the solution concept, and to have it, we say that a continuance function x is a mild solution of this nonlinear system if x satisfies such an integral equation where x0 is the corresponding initial condition. Since f is a Lipschitz continuance, one can, similarly to finite dimensional case, show that the solutions of the system exist and are unique, the mild solutions. Okay, so now we have our class of systems, and we now can define our stability property. And we will say that this semi-linear equation is uniformly globally asymptotically stable if there is a function beta such that we have such a high L estimate. Now, in infinite dimensional setting, this is not equivalent to local stability plus global attractivity. And now this is a stronger property, because just global attractivity does not tell us that the solutions corresponding to different states converge with a uniform speed. It is no more the case. And therefore, we study the uniform global asymptotic stability. And now, again, our main tool will be a Lyapunov function, how to analyze this property, and it is defined precisely in the same way as we have done for ODEs. The only difference is that now this function V acts on an infinite dimensional space X. And we have again a theorem, which is in particular, well, I cited you to Henry, which tells that this semi-linear evolution equation is uniformly globally asymptotically stable if and only if there is a Lipschitz continuous Lyapunov function for it. So the only difference to the ODE case is that now we do not have smoothness, but we claim only Lipschitz continuity. But it is enough for applications. So basically, we have a very, very nice tool how to analyze stability of nonlinear systems. So it seems that this completely solves our problem. The only thing is how to find this Lyapunov function for particular systems. However, now let us look at the tools which the researchers in linear systems theory are using to analyze stability. So now we forget about our nonlinearity F, and we consider just linear systems, and A is as previously a generator of a strongly continuous semigroup. So let X be a Hilbert space. Then Datko has shown that this system is exponentially stable, which is the same as uniform global asymptotic stability for linear systems. So this system is exponentially stable if and only if there is a positive self-adjoint operator P, bounded operator, which satisfies the Lyapunov equation, which we see here. So this is scalar product in X. Let us look at this result from the point of view of Lyapunov theory. Then we can define Lyapunov function in this way for all X. Then, since P is a positive operator, then we have that V is positive for all non-negative X. And since P is bounded operator, then we also have such an estimate. We can also, well, clearly V is a continuous function, and we can differentiate it along the trajectory, and we obtain immediately this expression. And thanks to the fact that P satisfies a Lyapunov equation, then we have such an estimate. So now V dissipates, so the derivative is negative with a given decay rate. So this shows that basically V is a kind of a Lyapunov function, and the only difference to our previous definitions is that we may not have here any nice bound from below. V is just positive definite, right? Well, by the way, it's not that we could not prove it. It really does not have to be coercive. I mean, it does not have to be such a bound. In particular, if A is a self-adjoint operator, then we can solve this equation, and the solution will be that P is minus A inverse over 2. And if the spectrum of A is unbounded, then 0 is in the spectrum of the operator P, and this means that indeed we will not have a nice bound from below here. We have only positive definites and not more. Okay? Well, fine, that was in Hilbert space. Now let us look what we have in a more general Banach space setting. Now X is a Banach space, and now we cite this result by Pazy, which is 3 years after Datko's theorem. Pazy tells us that this system is exponentially stable if and only if there is a number P from 1 to infinity such that the trajectory of our system is LP integrable for any x. Again, let us look at this from the viewpoint of Lyapunov theory. Then, again, we have that V is positive definite. Well, indeed, if x is non-zero, then this integral will be positive, will have positive value. And using Banach-Steinhaus theorem, one can obtain this nice bound from above for some a. After some work, one can show continuity of V, and also we can differentiate V to obtain the dissipation inequality. So we just do this by definition, we substitute our V, we change here the domain of integration, and then we obtain such an expression, and going to the limit when h goes to 0, we obtain precisely this expression, which means that again the energy dissipates and we have uniform decay rate here. So again, V is a kind of a Lyapunov function up to the fact that it is only positive definite, or as we will also say, non-coercive. Well, the final result which I would like to cite is the result by Littman, which extends Pazy theorem. Littman tells us that this system is exponentially stable if and only if there is some k function, so continuous function 0 and 0 and increasing, such that such an integral is finite for all x. So clearly we could take alpha as a power function, and then it would be a result by Pazy. But Littman is more general. But again, if we analyze it from the Lyapunov point of view, then we can define this as our Lyapunov function, and we obtain the same as before, that V is a kind of a non-coercive Lyapunov function. So what we have obtained? We have obtained that these classical criteria for exponential stability of linear systems due to Datko, Pazy, and Littman are actually the results about non-coercive Lyapunov functions. And now let us combine together what we have discussed till now. We have a nonlinear theory which tells us that all such systems with Lipschitz F are uniformly globally asymptotically stable if and only if there is some coercive Lyapunov function, any. And linear results which we have considered tell us that a linear system is uniformly globally asymptotically stable if and only if there is a non-coercive Lyapunov function of some particular type. Okay, so you see that these results are deep, although they are both about Lyapunov functions, but they actually very, very different. So here we claim coercivity, but of any Lyapunov function, and here it's okay to have non-coercive, but of some particular type. So there is definitely a big difference between them, and we would like to understand what is this difference. Is this coercivity needed? Maybe it's okay here to have just any non-coercive Lyapunov function to claim uniform global asymptotic stability. Maybe we don't need this any particular type. And maybe it's okay to have this non-coercivity here. Let us analyze this. Well, to start with, we need to define a non-coercive Lyapunov function, and we define it precisely as previously, and the only difference is that now we do not require this bound from below. Now V is just continuous function, which is positive definite, and the other things are as before. And now we have the following result, which was shown with Fabian Wirth in our GDE paper several years ago. And it tells us that this system is uniformly globally asymptotically stable if and only if three properties are satisfied. The first is that there is a non-coercive Lyapunov function, but that's not enough. We need in addition two further properties. We need that the flow map, our solution map, is continuous at the equilibrium. And in addition, we need that the flow map maps bounded sets in the bounded sets on finite intervals. So if we start from a bounded ball, and if we consider dynamics for finite time, then this means that all these all the states which will be passed by this bundle of trajectories, they all are within some big bounded block. Well, I would like to say that for this particular class of systems, actually, we always have this continuity of V at the equilibrium. But there are more general classes of systems, and this result in the paper was proved for considerably more general class of systems, and for them this condition is indeed needed. So here it is not necessary. And if F is globally Lipschitz continuous, then also this will be automatically fulfilled. So for globally Lipschitz F, uniform global asymptotic stability is equivalent to existence of a non-coercive Lyapunov function without any additional conditions. Okay, just some words about the proof. The linear results which I have presented, so the Datko result, Pazy theorem, Littman's theorem, their proofs are usually based on the use of Banach-Steinhaus theorem to get from some non-uniform properties to some uniform estimates. But here we cannot use Banach-Steinhaus theorem because because our systems are nonlinear. The Lyapunov theorem for coercive Lyapunov functions are proved by using of comparison principles. But here we cannot use them as well because we do not have any coercivity. And so we need a completely new strategy, and it is based on characterizations of uniform global asymptotic stability in terms of uniform weak attractivity, which was developed here and further improved in our other paper in CSS journal. Okay. Now, as a corollary of this general nonlinear result, well, let's say partially, so here we'll say a bit more. So what we obtain is that exponential stability is equivalent to existence of a non-coercive Lyapunov function. So I have told that this is valid actually also for nonlinear systems with globally Lipschitz F, and in particular, this is valid for linear systems. What do we also see here? Well, also exponential stability, well, is equivalent to existence of a coercive Lyapunov function. Well, clearly, this is also what we know. But also it is equivalent to existence of a quadratic non-coercive Lyapunov function. This means that if the system is exponentially stable, we can always find quadratic but non-coercive Lyapunov function. So the next question which we wanted to study, I mean, since these quadratic functions are very nice and they can be easily differentiated, so this is a very good class of Lyapunov functions. So the question whether we can always find for an exponentially stable system coercive quadratic Lyapunov function. And this is what we would like to analyze next. And here is our result. If X is a Hilbert space and this system is exponentially stable, then we have the following. There is a coercive and quadratic Lyapunov function for this system, if and only if the semigroup T is similar to a contraction semigroup. So this means that we can have some similarity transformation, same for all T of T, which transforms T into a contraction semigroup. Furthermore, if the semigroup is analytic, then we can even find this Lyapunov function V explicitly, and this is our formula. Okay. So what we see here? We see here in particular that if we have an infinite dimensional Hilbert space, and then we can always find a generator A of an exponentially stable analytic semigroup such that there is no coercive and quadratic Lyapunov function. This is what can be shown. So this means that this requirement that this Lyapunov function must be quadratic and coercive is already somewhat restrictive. And there are systems where we cannot find such Lyapunov functions. So either we should refrain from having quadratic Lyapunov functions, and then we can always find coercive one. Or we should say, no, we don't want coercivity, but we would like to have quadratic Lyapunov functions. Then we can always find a non-coercive, but quadratic Lyapunov function. So just, I will not tell anything about the proof, but just think that this integral actually does not necessarily converge for analytic semigroups in general, for exponentially stable analytic semigroups. So if here would be the power less than 1/2, then it would converge, thanks to the classic, well, standard properties of analytic semigroups. But with 1/2, we really need the fact that T is similar to a contraction already to claim that this integral is well defined. Okay, so you may say that this is actually quite complicated Lyapunov function, and I mean, yes, so we have found it, but can we really use it? Well, at least I can tell you that it is not so complicated in some particular cases. And if A is self-adjoint, then actually this Lyapunov function takes extremely simple form. So our Lyapunov function is given by this integral. Now we just write down this definition in this form. Now since A is self-adjoint, then also the semigroup T is self-adjoint. We can put everything here, and also T we put here as well, and we obtain this integral. Afterwards, we just take integral inside of our scalar product, and we get such an expression. Then we can change the integration variable here, and we get such an expression. And finally, since A is a derivative, well, A applied to this guy acts as a derivative, then we can easily compute this, and we have this expression. So our Lyapunov function, which has this form for analytic systems, for the special case of self-adjoint operators A, is just the squared norm of x over 2. I just mentioned here that if the A is self-adjoint, we can also always find a non-coercive Lyapunov function, which looks like here, but now we need here the action of this operator. Okay, so basically we have here a clear difference between non-coercive Lyapunov function and coercive one. Okay, and now we go to the end of the first half of our talk, and here we can summarize our results. So for this nonlinear system, we have that uniform global asymptotic stability is equivalent to existence of a coercive Lyapunov function. But also it is equivalent to existence of a non-coercive Lyapunov function, provided that the flow is continuous at the equilibrium, and also the map phi maps bounded sets into the bounded sets. For linear systems, we have that actually exponential stability is indeed equivalent just to existence of any non-coercive Lyapunov functions. So we don't need any particular types. So indeed, exponential stability is just equivalent to existence of a non-coercive Lyapunov functions. But if we would like to have a coercive and quadratic Lyapunov function, then we can find it only if T is similar to a contraction semigroup. Well, to be sincere, so many practical systems satisfy this property. This means that for most applications, the semigroup is similar to a contraction, and thus it makes sense to search for coercive and quadratic Lyapunov functions. But we can always find such systems which do not satisfy this property and thus do not have coercive and quadratic Lyapunov functions. The results from this first part of the talk were proved in these two papers in 2019, and the results on coercive and quadratic Lyapunov functions, so these criteria, were shown in this paper with Felix Schwenninger quite recently, and I just submitted to MCSS a month ago. Now, this is the end of the first part of the talk, and now we move to the system with inputs. Now we consider also somewhat more general class of systems. Namely, we start with a triple. We say that our control system is a triple consisting of the state space X, input space U, and a flow map phi. And we call this triple a control system if it satisfies these properties. The solution map or flow map is forward complete. So for any initial condition and any input, the flow is defined for all non-negative time axes. And also each trajectory is continuous and satisfies the cocycle property. We need also several more axioms here, but they are almost always satisfied. I just tell that ordinary differential equations, many classes of evolution PDEs with Lipschitz nonlinearities, broad classes of boundary control systems, time delay systems, and also so-called heterogeneous systems with components of distinct type are also all within this class of systems. So it is quite general. And we would like to analyze stability for this class of systems. And first of all, we start with our main concept for the second part of the talk. And this is input to state stability, introduced by Eduardo Zonta in 1989. So Zonta tells us that the system is input to state stable if and only if the norm of the trajectory is upper bounded by a sum of two functions. The first is scale function beta, which we have already seen previously, and it characterizes the transient behavior of the system, and it decays to zero when time goes to infinity. And the second term here is a so-called asymptotic gain, depending on the norm of the input solely, and it tells us the asymptotic deviation of the system from the origin. Really, I mean, if time goes to infinity, this guy goes to zero, and our trajectory is upper bounded by this guy. So if U is zero, if there is no input which is applied, then this term vanishes and our trajectory is upper bounded by this guy. And this is our situation here. So this means that any input to state stable system is uniformly globally asymptotically stable if no input is applied. If U is non-zero, then there is no guarantee that we will converge to zero. But our trajectory typically will look like that. So we are always under this bound, and we converge, at least asymptotically, to the ball with the radius gamma of norm of U around the origin. And this feature, that input to state stability unifies both stability with respect to initial conditions and robustness with respect to inputs, has made ISS a very appealing paradigm for analysis of stability of such systems with inputs. Well, it's not only this mathematical appeal, it's also very important for engineering applications. In particular, many methods for systematic design of robust controllers for certain classes of nonlinear systems are based on the ISS framework. Also, ISS can tackle very nicely the control problems in presence of quantizations, time delays on model dynamics, and some event-based techniques, etc., which are important for implementation of controllers to the practical systems. Also, ISS is essential for robust observer design and observability and detectability of nonlinear systems, and for analysis and control of large-scale networks. There is currently a vast literature on input to state stability, and here I have listed the survey papers and monographs devoted to this topic. So everything starts with a survey by Eduardo Zonta from 2008, and the most recent is the book by myself on input to state stability, which you also see here, which appeared just in the beginning of this month. Okay. Now we have our class of systems, we have the stability property, which we would like to analyze, and we need again a tool. And we again would like to apply the Lyapunov methodology. So we define coercive ISS Lyapunov functions in a similar way as previously for dynamical systems. But now we have inputs, and these inputs may move the system out from the equilibrium. So therefore, the difference is now in this dissipation inequality. Now this derivative of v with respect to trajectory is not always negative, but it's upper bounded by this term, which describes, let's say, the internal dissipation due to dynamics of the system. But we have also this addition and term characterizing the influence of external inputs. If the norm of the input is small enough, then this term dominates, and therefore the Lyapunov function decays along the trajectory. But if u is large with respect to the input, with respect to the state x, then this term dominates over the dissipation term, and the derivative of a Lyapunov function may be positive along the trajectory, and so the state may grow as well. So, our question for the second part of the talk will be to analyze the applicability of Lyapunov functions to ISS analysis. So again, there are several questions. There are direct Lyapunov theorems showing how we can prove input to state stability. There are converse theorems, which we would like to know whether Lyapunov functions exist at all if the system has ISS properties. And it is important to have some particular constructions of Lyapunov functions, which help us to prove the results for particular systems. We have several good news here. Well, first of all, the existence of a coercive ISS Lyapunov function implies input to state stability. And this can be shown in this similar way as for finite dimensional systems. Also, we know that if the nonlinearity f is a Lipschitz bounded balls, then at least for this class of infinite dimensional systems, which falls into the scope of that abstract systems I have defined previously, well, so for these systems, if f is Lipschitz in both x and u, input to state stability is equivalent to existence of a ISS Lyapunov function. Well, and it was proved by Fabian Wirth and me in our SCL paper several years ago, and it is based on the classical paper by Sonntag-Wang, where they have proved this result for ODE systems. Okay, we have also another kind of good news. Well, okay, let me tell here one thing. Yes, so this is a converse Lyapunov theorem, but f should be Lipschitz continuous in x and u. And although this is nice and satisfies the needs for many systems with distributed controls u, but for boundary controls, usually this function f does not have continuity even with respect to u. And therefore, although this result does not cover the boundary control systems, and they have to be considered separately, and I will tell more on this later. Okay, anyway, we have some other type of good news, namely that Lyapunov functions have been successfully used for hyperbolic systems, parabolic systems with boundary and distributed controls. And we have many motivating results in this direction. Nevertheless, there are also distressing but very motivating news. So, namely, the classical coercive Lyapunov methods failed to address the input to state stability of a linear heat equation with Dirichlet input. So this is a very simple system, just a linear heat equation with 0 at one boundary, which is very good, it helps us, and input u at the other boundary. And we know that this system is input to state stable. It was shown by 3 different methods, but at the same time, no coercive Lyapunov function is known for this system. And well, this is like a nightmare. Just think. Lyapunov function is usually the only method which the people studying nonlinear systems have in order to prove the stability of some particular systems. And now this method fails, or at least we don't know how to apply it, for a linear system and of, well, quite nice nature. And it's important to know the reasons why it is so. And clearly, I mean, we are not interested in only in this particular one system. We would like to have methods how we can treat input to state stability by Lyapunov tools for general boundary control systems. So let us analyze this more. Yeah, but before I do this, I would like to say that this failure of Lyapunov methods has led to thriving of non-Lyapunov methodologies. So we have the spectral method advocated by Karafilis and Krstich. We have methods of semigroup and admissibility theory, which were applied in particular in this paper by Jakob, Nabiul, Partinger, and Schwenninger. There is method of monotone control systems by Karafilis, Krstich, and myself. And there is this paper by Zheng and Zhu where the Georgi iteration has been applied to study ISS with Burger's equation. So these methods are really nice, but they are applicable only to some particular types of control systems. And we would like to go back and we would like to have the generality of the Lyapunov method. And so we need to study this more. Okay, so again, as in the first part of the talk, we define the non-coercive Lyapunov functions. So our function V is a non-coercive ISS Lyapunov function for a general control system if V satisfies these estimates. So again, this is the same as the definition of non-coercive Lyapunov function for systems without inputs, but now we have this influence of initial condition. Okay, so I assume here that the inputs are piecewise continuous, so this guy makes sense here. Okay, so and now we have again our main questions. We start with our direct non-coercive Lyapunov theorem. And what we can show, we can directly extend there is non-coercive result from the first part of this talk to input to state stability, to systems with inputs. And we show that if the system sigma has bounded finite time reachability sets, and if the flow map is continuous at 0, then existence of a non-coercive ISS Lyapunov function implies input to state stability. And again, we cannot use linear methods, we cannot use comparison principles, and what we can do is to base the proof on characterizations of input to state stability in terms of weaker properties like uniform limit properties. So these characterizations of ISS have been developed in these papers, so here for local ISS and here for global ISS. And in this paper, this non-coercive theorem has been proved. Okay, now how we can construct such non-coercive Lyapunov functions for linear systems? Before we proceed to this question, let us define what are linear systems in our case. So we consider systems x dot equals ax plus bu, and A is, as previously, a generator of a C0 semigroup, strongly continuous semigroup on a Banach space X, and B is an operator which is unbounded as an operator from U to X, but it is a bounded operator from U to a larger space X minus 1, which is called extrapolation space and is a completion of X with respect to this norm for some beta from the resolvent set of A. So T, well, there are several nice news. Well, first of all, B, all natural operators B, which appear in practice, they are of this form. So if B is unbounded even from U to X minus 1, then it is a too-bad operator B, and we have no hope to have well-posedness of such systems. So it is not a restriction at all. It's natural to assume. Also, our original semigroup generated by A can be extended uniquely to a semigroup on this larger space X minus 1. And we can also extend a generator to some operator A minus 1. So this means that we can consider this system not in X, but in X minus 1. And in this space X minus 1, the situation is very nice because B is now a bounded operator. And since it is a bounded operator, we can apply the variation of constants formula to represent our solution. And that's what we have here. That's our variation of constants formula. So looks very nice. The only bad thing is now that this solution is in x minus 1, because we have interpreted this in x minus 1. So the solution is also in this space. And now but we don't want to have solution here. We want the solution staying in x. And so now we would like to impose more restriction on B such that this guy, well, if we choose x0 from x, then this guy is from x. But to ensure that this integral is in x, we need to assume more on B, right? Because what we integrate is still in x minus 1, but the result should be in x. So what we introduce is the concept of Q-admissible control operators, and we say that such an operator B is Q-admissible if for all inputs U from the LQ space, the trajectory is well defined for all initial conditions and all times. Okay, so basically Q-admissibility of operator B is a well-posedness of a linear system for inputs from LQ. And now we have a result due to Jakob, Nabil, Parsenka, and Schwenninger, which tells us that a linear system is LQ ISS if and only if the semigroup generated by A is exponentially stable and the operator B is Q-admissible. So the system is well-posed. So ISS is well-posedness plus exponential stability of the semigroup. Okay, so it tells us a very nice criterion which can be used to show input of state stability. But this is a criteria for linear systems. And what we would like in the end of the day is to study nonlinear systems as well. And to study nonlinear systems, we need Lyapunov functions. And so what we would like now to do is to understand how the Lyapunov functions for such system may look like. And then, having such Lyapunov functions, we can try to see whether we can use them for nonlinear systems. And here is our result. So if we have this linear system, sigma, we assume that A generates a C0 semigroup, then what we have? If an operator P, bounded operator, satisfies these four properties, so these first two ones are needed to ensure that the system without inputs is exponentially stable. But in order to have also stability with respect to inputs, we need these two properties, which help us, let's say, to counteract with internal dynamics and cancel this unboundedness of B. So under these conditions, we have such a quadratic Lyapunov function, which is then we can show that it is a non-coercive ISS Lyapunov function for our linear system for any infinite admissible input operator B. In particular, then this is input of state stable. This system is input of state stable for this operator B. Again, as a special case, we like to state a result for self-adjoint operator A. Then it simplifies a lot, and we have the following result. Linear system in a Hilbert space where A generates a C0 semigroup and B is infinite admissible. If A is self-adjoint, then this is an ISS Lyapunov function. Well, so we have had only theory. Let me show you how we can compute Lyapunov functions for some particular systems. So first, we consider the heat equation with a Neumann boundary control. So U is here. And here we have Dirichlet conditions at another end, just 0. So it can be reformulated in this abstract framework as a linear system in a Hilbert space L2. Then we can take a Lyapunov function as a square L2 norm of x, and we can find dissipation inequality for these. To this end, we differentiate v along the trajectory. We have such an expression. Now we integrate it by parts, and we obtain such an expression. Here, this second term is already nice. It is negative quadratic term. But this term is not so nice because, first of all, it can be destabilizing, but also here we have a mixed term of x and u, and we would like to detach x and u from each other. So we apply, therefore, here for this term, the Young's inequality with some positive epsilon. So then we have such a bound, right? And now to this first term, we apply also Agmon's inequality. And then we have such an estimate. So what we do now we need to choose epsilon small enough. Then this bad term, positive, can be cancelled by this guy, right? Because here we will have larger coefficient. So then we combine this term with this term and apply Friedrich's inequality. Well, okay, Poincare inequality in this case. And we obtain this estimate then. Then we can also cancel this bad guy with this good one. And we obtain in the end such an expression. And it tells that actually the system is input to state stable for inputs from L2 space, which can be shown by our coercive Lyapunov results. Okay, so in particular, V is a coercive L2 ISS Lyapunov function. Now let us look to the same equation but with Dirichlet input. Again, we can reformulate it in an abstract fashion, and we can consider a Lyapunov function. Again, we take squared norm, we can differentiate, we can integrate by parts, we can then detach x and u from each other by Young's inequality if we like. But the problem is that we don't know how to bound this derivative of x at 1 by Lyapunov function or some nice expressions, and that's a problem. At least till now, nobody has come up with an idea how we can show that this or some other Lyapunov function is an ISS Lyapunov function for this system. So we have no coercive Lyapunov functions for that. But it was shown that this system is ISS by 3 different approaches, by the stability approach, spectral analysis, monotone methods. So it can be shown. And now, with the previous results which I have shown, we can say that this system is at infinity ISS, and we can construct a non-coercive ISS Lyapunov function in this way. So clearly our operator A is self-adjoint here, well, the Dirichlet Laplacian, and we construct B in this form. It's definitely non-coercive, it is not a coercive function, but now we have a Lyapunov function for this system. Still, it is interesting, when do we have coercive quadratic Lyapunov functions? Because, I mean, non-coercives are good, but maybe we can come up with the classical constructions. Let us analyze this. We have here such a result, which is the main result of this MCSS paper submitted with Felix Schwenninger a month ago. So what is our setting here? We assume that A generates an exponentially stable analytic semigroup, and T is similar to a contraction. Well, as we have seen from the first part, if the semigroup is not similar to contraction, then we cannot find coercive and quadratic Lyapunov functions. So we need to assume this if we hope to have something coercive and quadratic. But now we also need to assume something on our operators B, and we assume that they are bounded operators from U to some spaces x minus p, where it is defined here. Okay. So we have already seen the space x minus 1, that it is much larger than x. So this space is x minus p, where p is something between 0 and 1. They are between x and x minus 1. So this operator is definitely unbounded from u to x, but it is much nicer than just bounded from u to x minus 1. And under this condition, we can show that this Lyapunov function, which we have already seen previously, is a coercive quadratic L2 ISS Lyapunov function for this system. In particular, then this system is ISS for L2 inputs. Well, just let us compare this result to this criterion of L2 ISS. So if we would like to have L2 ISS, then it is the same that to claim that T is exponentially stable and B is too admissible. Okay, yeah, and so here we also say that A must be exponentially stable, and we restrict our results to analytic semigroups. But also we know that we must assume that T is similar to contraction to have coercive quadratic Lyapunov functions. So it's also not a restriction. So the only real difference, so let's say the real gap between where it can be a bit improved is that here we claim something more than true admissibility, but it's only a bit more, it's not that much. So we have some gap between these results, but it is not high. So it is, let's say, almost final converse Lyapunov theorem for such analytic semigroups, which are similar to contraction. If A is self-adjoint, then we again have some improvement. So if A is self-adjoint and it generates exponentially stable analytic semigroup, then if B is from this space, which is a bit better than previously, but still a bit more restrictive than to admissibility of B, then under such a condition, just this simple Lyapunov function is the coercive quadratic L2 ISS Lyapunov function. And then the system is L2 ISS. This covers that example of Dirichlet equation with Neumann boundary conditions. So here we come to conclusions. So in the second part, we have discussed coercive ISS Lyapunov theorems, as well as non-coercive ISS Lyapunov theorems. So we have shown that if we have a non-coercive ISS Lyapunov function, then we can show input to state stability if we have additional regularity of the flow map at 0 and boundedness of reachability sets. Also for linear systems with admissible input operators, we have derived converse non-coercive Lyapunov results and also converse coercive quadratic Lyapunov theorems. So overall, the main references for this talk are these two papers with Fabi and Wirth, where we have developed the theory of non-coercive Lyapunov functions for dynamical systems. In this paper, we have proved the non-coercive results for input to state stability. And here we have analyzed the coercivity of quadratic Lyapunov functions for linear systems with Felix Schwenninger. So, and here you can see also my book, which recently appeared by Springer, and here it's mostly contains finite dimensional, so ISS theory for ODE systems, but there are also some chapters devoted to infinite dimensional theory as well. So on here, I thank you a lot for your attention, and here you can see papers and slides at my homepage. So thanks a lot for listening to this, and have a great day.